In mathematics, a function f from a set X to a set Y is surjective, or a surjection, if every element Y in Y has a corresponding element X in X such that f equals Y. The function f may map more than one element of X to the same element of Y. The terms surjective and the related terms injective and bijective were introduced by Nicolas Bourbaki, the pseudonym for a group of mainly French 20th-century mathematicians who wrote a series of books presenting an exposition of modern advanced mathematics. Beginning in 1935, the French prefix sur means over or above and relates to the fact that the image of the domain of a surjective function completely covers the function's codomain. Definition: a surjective function is a function whose image is equal to its codomain. Equivalently, a function f with domain x and codomain y is surjective if for every y in Y there exists at least one x in X with. Surjections are sometimes denoted by a two-headed rightwards arrow, as in f, x, y. Symbolically, if then is said to be surjective if. Examples: for any set X, the identity function IDX on X is surjective. The function f z 0, 1, defined by f equals n mod 2 is surjective. The function f r defined by f equals 2x plus 1 is surjective, because for every real number y we have an x such that f equals y. An appropriate x is 2. The function f r defined by f equals x3 minus 3x is surjective, because the pre-image of any real number y is the solution set of the cubic polynomial equation x3 minus 3x minus y equals 0, and every cubic polynomial with real coefficients has at least one real root. However, this function is not injective since e.g., the pre-image of y equals 2 is x equals minus 1, x equals 2. The function g r defined by g equals x2 is not surjective, because there is no real number x such that x2 equals minus 1. However, the function g r 0 plus defined by g equals x2 is surjective, because for every y in the non-negative real codomain y there is at least one x in the real domain x such that x2 equals y. The natural logarithm function ln r is a surjective and even bijective mapping from the set of positive real numbers to the set of all real numbers. Its inverse, the exponential function, is not surjective as its range is the set of positive real numbers and its domain is usually defined to be the set of all real numbers. The matrix exponential is not surjective when seen as a map from the space of all n times n matrices to itself. It is, however, usually defined as a map from the space of all n times n matrices to the general linear group of degree n, i.e., the group of all n times n invertible matrices. Under this definition, the matrix exponential is surjective for complex matrices, although still not surjective for real matrices. The projection from a Cartesian product A times B to one of its factors is surjective unless the other factor is empty. In a 3D video game, vectors are projected onto a 2D flat screen by means of a surjective function. Properties: a function is bijective if and only if it is both surjective and injective. If a function is identified with its graph, then surjectivity is not a property of the function itself, but rather a relationship between the function and its codomain. Unlike injectivity, surjectivity cannot be read off of the graph of the function alone. Surjections as right invertible functions. The function g yx is said to be a right inverse of the function f x y if f equals y for every y in Y. In other words, g is a right inverse of f if the composition fog of g and f in that order is the identity function on the domain y of g. The function g need not be a complete inverse of f because the composition in the other order, g o f, may not be the identity function on the domain x of f. In other words, f can undo or reverse g, but cannot necessarily be reversed by it. Every function with a right inverse is necessarily a surjection. The proposition that every surjective function has a right inverse is equivalent to the axiom of choice. If f x y is surjective and B is a subset of Y, then f equals B. Thus B can be recovered from its pre-image f-1. For example, in the first illustration, there is some function g such that g equals 4. There is also some function f such that f equals c. It doesn't matter that g can also equal 3, it only matters that f reverses g. Another surjective function. A non-surjective function. Surjective composition. The first function need not be surjective. Surjections as epimorphisms. A function f x y is surjective if and only if it is right-cancellative. Given any functions g, h, y, z, whenever GOF equals HOF, then g equals h. This property is formulated in terms of functions and their composition and can be generalized to the more general notion of the morphisms of a category and their composition. Right-cancellative morphisms are called epimorphisms. Specifically, surjective functions are precisely the epimorphisms in the category of sets. The prefix epi is derived from the Greek preposition pi iota meaning over, above, on. Any morphism with a right inverse is an epimorphism, but the converse is not true in general. A right inverse G of a morphism F is called a section of F. Imorphism with a right inverse is called a split epimorphism. Surjections as binary relations. Any function with domain X and codomain Y can be seen as a left total and right unique binary relation between X and Y by identifying it with its function graph. A surjective function with domain X and codomain Y is then a binary relation between X and Y that is right unique and both left total and right total. Cardinality of the domain of a surjection. The cardinality of the domain of a surjective function is greater than or equal to the cardinality of its codomain. If f x y is a surjective function, then x has at least as many elements as y, in the sense of cardinal numbers, equals y for all y in Y exists. G is easily seen to be injective, thus the formal definition of y, x, is satisfied. Specifically, if both x and y are finite with the same number of elements, then f x y is surjective if and only if f is injective. Composition and decomposition. The composite of surjective functions is always surjective. If f and g are both surjective, and the codomain of g is equal to the domain of f, then fog is surjective. Conversely, if fog is surjective, then f is surjective. These properties generalize from surjections in the category of sets to any epimorphisms in any category. Any function can be decomposed into a surjection and an injection. For any function h, x, z, there exists a surjection f x, y and an injection g, y, z such that h equals GOF. To see this, define Y to be the sets h-1 where Z is in Z. These sets are disjoint in partition X. Then F carries each X to the element of Y which contains it, and G carries each element of Y to the point in Z to which H sends its points. Then F is surjective since it is a projection map, and G is injective by definition. Induced surjection and induced bijection. Any function induces a surjection by restricting its codomain to its range. Any surjective function induces a bijection defined on a quotient of its domain by collapsing all arguments mapping to a given fixed image. More precisely, every surjection f a B can be factored as a projection followed by a bijection as follows. Let A tilde be the equivalence classes of A under the following equivalence relation. X tilde Y if and only if F equals F. Equivalently, A tilde is the set of all preimages under F. Let P A tilde be the projection map which sends each X in A to its equivalence class X tilde, and let A tilde B be the well-defined function given by A equals F. Then F equals A rho P.